Hi, today I'm going to tell you about efficient interactive coding over the binary channel, achieving optimal error resilience. So my name is Meghal Gupta, and this presentation is based on joint work with in a paper with Rachel Zhang. Okay, so before we really get into anything, I'm going to define what I mean by interactive coding. So interactive coding is basically an interactive analog of error correcting codes. So we're just going to start there. So in the classical error correcting code setting, Alice has a message X that she's trying to send to Bob. But the channel is noisy. So there's allowed to be an adversary Eve who flips some of the bits that Alice sends over to Bob. So the problem here is that if even one of the bits is flipped, Bob no longer learns X correctly. So the classical way to solve this problem is with error correcting codes. So with an error correcting code, instead of Alice sending X directly, she's going to send ECCX, which is some function of X that Bob can decode to figure out X. And the guarantee here is that even if there's a constant fraction of the bits that are corrupted by Eve, Bob is still going to be able to figure out X as long as that constant fraction wasn't too high. And in fact, more precisely, this constant fraction is known as the error resilience, and the optimal error resilience that a code can achieve is 1/4. So codes are usually evaluated based on two important parameters. These two parameters are their error resilience and their length. So the error resilience, as we said earlier, 1/4 is optimal. For the length of the code, usually only codes are considered when they're linear in X. So the optimal codes are positive rate, which means that the blow up relative to the length of X is only linear, is only a constant factor. So it's well known how to get constant factor blow up for the setting. And in fact, most of the work is on optimizing actually what this rate is. But for this talk, anything that's positive rate is going to be considered basically equally good. So now we're going to talk about the interactive analog of this definition of error correcting codes and how the parameters play into that setting. So in the interactive setting, again, Alice has an input X, but this time Bob also has an input Y. So Alice and Bob are engaging in a protocol jointly, and the goal of their joint protocol is to compute some function f of x comma y and output it, and both output it at the end of the protocol. And they've only succeeded if both Alice and Bob correctly output f of x comma y at the end of the protocol. So to give a little bit of a concrete example, this is an example of an interactive protocol. So Alice's input is her chess strategy. Bob's input is his chess strategy. They're both, let's say, deterministic strategies. So then an example of the function f of x comma y that they might want to compute is when they play a chess game against each other, who wins if Alice goes first? So the way they would compute this is they would just play a chess game. So Alice would send over her first move, Bob would send over e4, and then Bob would send over his response to e4, which might be e5, and they would continue playing a chess game like this. They can jointly engage in an interactive protocol and both at the end figure out who won the chess game, and then they would successfully both output f of x comma y at the end. So let's go back to so I guess now that we have a little bit of sense of this, let's go back to the general let's go back to the general variables here, where Alice has an input x, Bob has an input y, and their goal is to compute f of x comma y. So as before, we're trying to define error correcting codes here. So we're trying to define what the noisy setting is. So in the noisy setting, the adversary Eve has a budget to corrupt up to alpha fraction of the total bits sent by either party. So now we have a protocol that could be super, super long, super, super weird in terms of number of rounds of communication, length of different messages and whatnot. And the adversary, their only restriction is they can only corrupt up to alpha fraction of the total bits sent. So for example, they could, let's say this is a super long protocol, so not just 3 messages. They could just take message 2 and replace it with completely random bits. So I guess the point is in the previous slide, the point here is that the goal is for Alice and Bob to modify their protocol such that they are resilient to this happening, so that they successfully both output f of x comma y, even if Eve is able to corrupt alpha fraction of the protocol in this way. So I guess, for example, one thing to be aware of here is that Eve may delete the entirety of message 2, Eve may delete the entirety of M2, but somehow throughout the rest of the protocol, Alice and Bob need to be able to notice that and like recover the fact that like M2 was corrupted, and like they need to learn what M2 was anyway. So I guess like let's define it a little bit more formally, maybe then it'll be clearer. So the setup is as follows. Alice has an input X, Bob has an input Y. They both want to compute f of X comma Y. Alice and Bob are allowed to send messages in a pre-designated order, and the goal is to output f of X, Y at the end. And they are said to be successful if they do this. The protocol is alpha error resilient. If they succeed correctly, whenever Eve corrupts at most alpha fraction of the bits sent by either party. So like of the total bits sent. So Eve corrupts less than alpha fraction of the total bits sent, then Alice and Bob will be able to successfully determine f of X comma Y. So the efficiency of such a protocol is measured with respect to some pi naught that computes f of X comma Y in the zero noise setting. So this is kind of analogous to regular error correcting codes in that the efficiency is measured against the message X, the length of the message X itself, which is sort of the best way for Alice to send Bob X in the setting with no noise. So in this setting, like sort of like X is sort of like the thing you're trying to communicate X is the noiseless protocol pi naught. And the goal is to not be much worse than the noiseless setting. So, okay, so I guess we're gonna get a little bit of sense for interactive coding by figuring out some fake protocols for interactive coding. So the first fake protocol we're going to think about is the following. Sorry. So remember that like in the noiseless protocol, Alice was sending M1, Bob was sending M2, and then Alice was sending M3 and so on. So what if we just modify this protocol as follows? We just have Alice send ECC of M1, Bob send ECC of M2, and then Alice send ECC of M3 and so on. So the problem here is that like Eve is allowed to, so let's say that this is lots of messages long, not just 3 messages long. So the problem here is that Eve can just like take one of the messages, let's say M2, and corrupt it entirely. Just replace ECC M2 with completely random bits. Then Bob and Alice will not be able, then Alice will not actually learn M2, and she'll never know it for the rest of the protocol. And so the rest of the protocol will all be out of whack, even though only the only amount of the protocol corrupted was just like 1 over the total number of messages sent, which could be like growing in n. So it could be like much larger than a constant fraction. So I guess the point here is that like the amount of bits being is that an important distinction here is that like Eve's budget is to corrupt alpha fraction of the total protocol. But that definitely means she can corrupt more than alpha fraction of an individual message, which is sort of like the difficulty of interactive communication. So the solution that we'll need to have will sort of need to have the property that later in the protocol, Alice and Bob will have some sort of self-correction measure to realize that, okay, M2 was wrong a long time ago. So that's why like this solution doesn't work. The second solution, which actually kind of works in a very fake way, is Alice sends ECCX to Bob, and then Bob sends ECCY to Alice. So what I mean by that, so this is resilient to 1/8 bit flips. What I mean by that is the following. If Eve has the budget to corrupt 1/8 of this protocol in total, then that means she has budget to corrupt less than 1/4 of each individual message, which means that Bob will successfully decode X and Alice will successfully decode Y. And then, they can on their own, once they know X and Y respectively correctly, they can themselves compute f of X and Y. And since there's no error in that, they'll definitely be correct. The problem with this protocol, so it does work. The problem with this protocol is it's very inefficient. So it doesn't satisfy that second property we said earlier, that we want only linear blow up in communication compared to the shortest protocol computing f of X comma Y in a noiseless setting. So, okay. So I guess as in the regular correcting code setting, there are 2 questions that we're going to ask. We're going to ask what is the optimal error resilience, and what is the best length of code you can get. So the solution we described on the previous slide can get 1/8, but this is actually not optimal. And even in the completely inefficient setting, getting the optimal bound is non-trivial, but we'll describe that later. And the second thing we're going to talk about is the length of the code. So we haven't even discussed yet whether it's possible to get linear for any possible value of alpha, but it turns out you actually can get it. And this is the result that we're going to discuss on the next slide. So the seminal result of Schulman in '96 said that there is an interactive coding scheme that simulates any noiseless protocol pi naught, and it uses O of pi naught bits of communication. And it is resilient to a really small but constant fraction bits flipped by an adversary. On the other side of this, there's the optimal error resilience. So a result of Gupta and Zhang in STOC 2022 says that there is an IC protocol resilient to 1/6 bit flips, but with exponential blowup in the total number of bits communicated. So the main goal of this talk is to combine both of these results. So get 1/6 error resilience while only incurring a linear blowup in communication. So I guess to summarize, here are the previous results. There's sort of two settings we've been talking about: inefficient and efficient. In the inefficient setting, there's the 1/8 protocol that I just described. Then this was improved to 5/39 in a paper by Efremenko, Cole, and Saxena in 2020. And then this was improved to 1/6 by Gupta and Zhang in 2022. On the other hand, in the positive rate side of it, even getting like 1/8 in that setting is pretty non-trivial and was shown by Braverman and Rao in 2011. And then the EKS paper does actually get positive rate as well. Also, like a 1/6 upper bound is known in both settings. The thing that was missing was the final piece, which is to get 1/6 in the positive rate setting. So that is the main result of this talk. So the rest of the talk I'm going to dedicate to explaining how the protocol works at a high level. Let's restate the problem just so we know what we're going for here. So Alice and Bob engage in so Alice has an input X, Bob has an input Y. They're trying to compute f of X comma Y. They engage in a fixed order, fixed length protocol in order to do this. And the goal is to construct an efficient protocol resilient to 1/6 adversarial errors. So the starting point we're going to need is the protocol of Gupta Zhang in 2022, which gets the 1/6, but not the efficient. So we're actually going to have to explain the general structure of that protocol in order to understand the modifications that we have to make in order to make it positive rate. So let's start with the 1/8 thing that we described earlier. Remember again that this is completely inefficient, so it's okay for Alice and Bob to be exchanging inputs here, even though that's like only allowed in like a very fake sense. So Alice sends ECCX, Bob sends ECCY. This is resilient to 1/8 corruptions because of the fact that each direction, so like Alice's communication to Bob or Bob's communication to Alice, individually, those are each resilient to 1/4 communication. So the thing we're going to want to do here is to make each person's messages resilient to 1/3 corruption instead of 1/4. So you can't do this with this exact setup because, like, as we said, ECCX is resilient to at most 1/4 corruption. But we're going to use interaction in order to make Alice's communication of her input to Bob resilient to 1/3 communication instead of 1/4. We're sort of going to do this by having Alice send X at the same time that Bob is sending Y and intertwine this in a way such that they are both giving feedback to each other. And then this feedback is going to help them get 1/3 error resilience. So let me describe this a little bit more concretely, at least. The general goal here is going to be just to understand the structure of the messages and not so much why the protocol works. So the general structure of the protocol is as follows. Alice is going to keep track of a guess Y prime for Bob's input, and her messages are going to look like the following. The message she's going to send is going to consist of two parts. The first thing is going to be her guess Y prime, which is her current guess for Bob's input Y. The second thing is an instruction. So the instruction is going to be as follows. Bob So Bob in the previous message to her, which is not illustrated above, sent a guess that he currently has for x prime, or sent a guess x prime that he currently is guessing for x. Then the second thing, then the second part of Alice's thing, which is D, is an instruction on how Bob should modify x prime in order to make it closer to x. What do I mean by that? So Alice is going to take Bob's guess x prime, and she's going to return one of four things. If the guess x prime is correct, she's going to return bullet as D and say that, like, okay, your guess is perfect, do not change it. The second thing she might do is say that, okay, you should append a 0 to your current guess. Like, your prefix is fine. You've sort of started constructing x correctly, but then you don't have any more bits, so you should append a 0, and then that'll be your new guess. The third thing she might say is append a 1 to your guess similarly, and the fourth thing she might say is your guess doesn't look good so far, just remove a bit from it. It's not super important what these guesses are, but the point is that the general idea is that instead of Alice directly sending x over to Bob, Bob is going to have a guess for x prime that he sends to Alice, and Alice is going to tell him how do you modify this guess. So I don't want, like, instead of Alice directly sending over ECCX, Bob is going to send guesses and Alice is going to send responses, like good or bad, or like exactly how bad, to Bob. So as a general summary, Alice's message consists of two parts. It consists of her guess for Bob's input, which he will provide instructions for how to modify. And then it contains instructions for how Bob should modify his current guess. So we're going to call this like a simultaneous question-answer procedure. It's a question-answer procedure in the sense that y prime is sort of a guess for what Alice thinks y is, and D is an answer to how Bob should modify his current guess x prime. So the reason that this has O of x squared communication is that each individual message sent is about x long, and it turns out in order to get Alice and Bob to converge to the correct answers, you need x rounds of communication, so that ends up being O of x squared total. So now I'm going to quickly talk about the modifications that we have to make in order to make this positive rate. So there's 3 steps that you have to do. The first is, instead of having O of x squared, we're going to modify the Q&A procedure to get O of pi squared instead, where pi naught is the length of the shortest, pi naught is the shortest noiseless protocol computing f of x comma y. The second step is going to be to use tree codes to go from pi squared to pi communication. And the general idea is going to be that in each round, Alice is only going to send a constant number of bits instead of like O of pi bits. And the third step, and like this actually succeeds at our goal of positive rate, but the third step is going to be computational efficiency. The protocol created by steps 1 and 2 will be O of pi communication, but Alice and Bob are going to be running in exponential or maybe even super exponential time. And we're going to use a boosting algorithm to get them to run in quasi-linear time. Okay, cool. So we're going to quickly talk about each of these steps. We're not going to go into super much detail on each one of them. So we're going to talk about the O of pi squared communication step first. So remember that, like in the protocol we described earlier, each of Alice's messages to Bob was y prime, sent both y prime and D, where y prime was a guess for what Bob's input is, and D was an instruction. So the instructions are going to look kind of the same, but now pi naught A is going to be Alice's guess for pi naught A is going to be Alice's guess for the transcript of the noiseless protocol. So it's going to be her guess for what the final transcript looks like in the computation of pi naught, where pi naught is like the noiseless protocol computing f of x comma y. So this idea of a transcript is common in interactive coding. Is common in interactive coding, but the modifications for how to get from how to adapt Gupta and Zhang's 2022 idea into this transcript setting are a little bit weird. And it's a little bit complicated to make something like this actually work, even though I'm not really explaining the details in this talk. So before I explain the O of pi squared to O of pi thing, we're going to have to do a quick digression into tree codes. So the general idea of a tree code is that Alice has an input X that's B1, B2, B3, dot, 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 and she's trying to send it in a streaming way to Bob. So like the thing she might do is send B1, B2, B3 directly, but the problem is that like the adversary can flip B3 and like then Bob will not learn X. So in a normal error correcting code, Alice knows all of X beforehand, so she can just encode this as ECCX. But in a streaming problem, like the first bit that Alice sends is only allowed to depend on B1. The second bit is only allowed to depend on B2 and B1. The third bit is only allowed to depend on B3 and B1. Formally, you need something that looks like this. You need the first thing that Alice sends to depend on B1, the second thing to be an encoding of B2 that can depend on B1, but not on like B3 and so on. And then you need to do something like this. So the loose guarantee of a tree code encoding is the following, that even if the ith message is incorrect, Bob will eventually learn BI. That is to say that like, even if T of B2 is flipped, then eventually after, let's say, hearing like 10 more messages, Bob will have a pretty good guess for what that B2 was corrupted, and he knows what it actually is. The reason he's able to do something like this is like the encoding of the future messages actually depends on B2. So it'll be inconsistent with what he heard for B2. So the more precise guarantee that we're going to need for the tree codes in this talk, which is actually a new guarantee compared to what previous discussion of tree codes obtains, which is that at every point after receiving the ith message, if the ith message was received correctly, so I guess I should note that each message here is a single symbol in a large alphabet, bit sigma. And the guarantee is that if Bob receives the ith message correctly, then he'll decode all of B1 through BI correctly. So if at any step Bob receives T of BI semicolon B1 through BI minus 1 correctly, then no matter how much corruption he's seen in the previous steps, even if like everything else was corrupted, he's going to be able to decode all of B1 through BI correctly, even though T of BI is only like a single symbol in sigma and not like a really long code. So for people who have seen tree codes, this is maybe a little bit of a weird guarantee, but so I should note that there's some caveats here and it's only true in a very approximate sense. But if you're more curious about it, feel free to email me and ask, or like read our paper. So I guess the modification for pi squared to pi is pretty simple from here. It's just instead of Alice sending ECC of pi naught at every step, she sends ECC of the tree code encoding of pi naught. And the reason she's able to do this is that every step her guess for pi naught only changes by 1 bit, since it can only change by like adding a 0, adding a 1, or rewinding. And whichever one of these she does, she just like sends the tree code. She just sends that particular like change in the form of a tree code. I'm also going to note that we actually have to use something slightly different than tree codes called layered codes, which are low memory analog of tree codes, but I'm not going to cover it in this talk. The final step of our protocol is computational efficiency. So as I described earlier, the protocol so far is actually going to be very inefficient. Largely, this is because constructing tree codes is not known how to be done in an efficient way. So there's actually a really nice property here, which is that there's a black box transformation of any IC protocol that makes it go from computationally inefficient to computationally efficient without increasing its communication complexity and while preserving its error resilience. So it was shown that you can do this in Ghaffari Hoppler in 2013. However, their protocol blows up the alphabet size of the protocol. So our contribution is a transformation that preserves the alphabet size. This is important because we're working in a binary alphabet, whereas they were working in like a large alphabet size. So it was okay for them to blow up the size of the alphabet a little bit. So as a summary, the positive rate modifications we needed were first we were getting from over the work of 2022 was the first step was getting to pi squared, and the second step was getting from pi squared to pi, and the third step was getting computational efficiency. So that's basically it. I guess before we leave, I want to remind you, if you go away with anything, to remember the statement of the result. The statement of the result is that we can get optimal error resilience and efficient interactive communication simultaneously, whereas before they were only known how to be done separately. And I guess the final thing I'll talk about is some open questions. So in some sense, this work is more of a work that closes a direction. So I wouldn't say that so I think the most of the open questions are not like super related to this work. The first one is about handling errors and erasures simultaneously. So there's a known protocol that gets 1/2 resilience to erasures. So the question is, and this protocol gets 1/6 resilience to errors. So I guess there's a question of, can you do that like simultaneously? Can you get a protocol that handles 1/2 fraction of erasures, that handles, 1/2 fraction of the quantity erasures plus 3 times errors? Some intuition for why this might be possible is in the one-way communication setting. You can get something that handles 1 fraction of the quantity erasures plus 2 times errors, which is sort of more reasonably tight, because you can handle 1/2 fraction of erasures and 1/4 fraction of errors simultaneously. The second question is, can you do this sort of thing for different alphabet sizes? So our protocol here is optimal for binary. Our protocol here is optimal for binary, and like in the asymptotic case of like large alphabet size, the answer is known to be 1/4. But like, what about for specific sizes like ternary or fourary? Can you get the exact answer for those? And the final question is not really a question about error resilience, but just about IC in general. Can you find an efficient positive rate deterministic protocol? Currently, no protocols receiving any constant rate are known that are deterministic and positive rate and efficient. There's progress in BKS 2020 that says that deterministic IC is possible, conditioned only on the construction of efficiently encodable tree codes rather than efficiently decodable tree codes, as was previously necessary. All right, thank you. So that's basically it for my talk. Email me if you have any further questions, and I hope you have a good day.